By looking at the credit analysis problem, we can see that there's actually three different types of learning problems. The first problem is to decide for a credit application whether to approve or deny the request. This is a binary classification problem, and we've learned one algorithm to do that, which is the perceptron learning algorithm. This returns a value of either +1 or -1, whether the classifier thinks it's part of the positive class or the negative class. Today we're also going to look at the second problem, which is to decide the amount of credit or credit line that somebody might get, given a credit analysis. This is a real valued problem output, so we're going to call this a regression problem. The regression problem is going to return a real valued output. The final problem that we'll examine is still a binary classification problem. However, here, instead of just getting out the binary classification, we want to also know the probability of the event happening or not. For example, we might want to know the probability that the customer will default on their loan. This is a logistic regression problem that's going to output a probability value between 0 and 1. We're going to start with regression and come back later to logistic regression. So to start off our investigation on linear regression, let's go back to the credit approval problem that we've seen several times. Now we want to ask ourselves, how much credit do we want to extend a particular person who's filled out a credit loan application? We still might have the same type of information that we'll go on, just as we did for the credit approval process. We started off with the classification problem that we looked at last week, which is to decide whether to approve or deny the credit application. But today we're going to be looking at the real valued output that we want to extend in terms of a dollar amount, what type of credit line we want to offer the customer. This is a regression problem, distinct from the classification problem. So the input we said is already going to be the same as what we've seen before. And the important thing here is we're going to get, and linear regression is just going to use the inputs and weight them by coefficients. And it's going to do that by assigning a different weight to each of the features. We've also written this in a vector format, where we're just taking the transpose of the weight vector and timesing it by the vector that represents the observation. If you don't like the vector format, you can always go back to the original formulation, which is for the individual variables. Just remember that we have a bias term that we are going to start with that has an observation of x0, whereas the other input features have their own coefficients, all the way to the nth one. So what's the training data that we're going to use to decide the weight vector theta? Well, it's going to be based on historical data of what the bank has already approved for past credit lines, based on customers that it did actually approve or ones that it rejected. It could be the first customer application, the second, the third, all the way to the nth one. And again, just to make sure we're clear about this, to be different from the classification case, our target output is going to be real valued. It's the actual amount of credit that we're going to try to extend for a particular customer. And regression is trying to replicate this by setting its values of theta to replicate it as best as possible. So how are we going to set theta? We're going to do this based on how well the actual signal, as represented by theta transpose x, is going to approximate f of x, the true value from the training data that we have from the historical examples. So we'll go through all of the training examples and use whichever setting of theta that we have currently, times it by the training data, and find the value, and then check whether that's going to come close to f of x. So in linear regression, we can use any type of error as a cost function, but typically we use squared error because it's convenient and it represents the idea that errors that are pretty far off are pretty bad and that small errors are forgivable. So when we want to write a training error or cost function, we'll write something like this. Here we're using capital J to denote the entire cost function. So what do you think should go inside of this? Well, we have to take the squared error first. Which is going to measure how bad our hypothesis is compared to the actual ground truth, and to square the error to say that big mistakes are very costly. And that's the error on just the JF training example, so we're going to have to take the average of this. To do that, we're going to first take the sum and just divide through all of the magnitude of the training examples. We've written it up for you here so it's more clear. Now let's look at an example of linear regression. Here we have a univariate case where we've plotted some values of a single variable x and the real valued output that it maintains. You can see the variable is inversely correlated with the outcome. For example, x might represent the amount of time that you spend on activities other than studying for machine learning, and y might represent the score that you get on your midterm. In linear regression, we're just drawing a hyperplane to try to match the dots as best as we can. So we might draw something like this. In this case, we can say that our hypothesis is going to be made up of a bias term plus one coefficient for the x. We can think of the theta 0 as the intercept, and theta 1 as the slope of the hyperplane. Of course, in 2D, this is just a line. We could draw many such types of lines, even one like this, and our job is to find an algorithm that's going to be iteratively able to optimize our weights until we can get something like the original red boundary that I drew. Let's now clean up the diagram and draw a line so that we can illustrate the idea of cost. By cost, what we mean is how bad is the values that our learned model has come up with compared to the actual values of y. So they're going to look a little bit like this. You can see this one is particularly bad. So we'll be squaring all of these different lengths here and summing them together to get a cost for this particular set of theta. Of course, this isn't limited to a single univariate calculation like we saw just now, where we only have a bias term and a single variable. We can extend it to a multivariate case. On the right, we're showing a two-dimensional plane where the data points might be projected onto an x1, x2 plane. We're not limited to one or two dimensions. It could be any n-dimensional case, in which case linear regression is trying to find a hyperplane of dimensions n minus 1.